So intermolecular forces are pretty simple if you already understand how dipoles and molecular dipoles work. It's essentially just a magnetic attraction between molecules. So if you have a polar molecule, it's going to attract other polar molecules. And there are three main ways that molecules can attract each other. The first is called dipole-dipole force. It's an attraction between polar molecules. So for example, if I have carbon monoxide and it has a dipole towards oxygen, then I have another carbon monoxide close to it, there's a very specific way that these two are going to interact because they both have these dipoles, right? So the dipole essentially means that this end is partially negative and this end is partially positive. And you saw those signs when we talked about dipoles earlier. The same thing is true over here. We have positive on the left, partial negative on the right. And since that's the case, these two things, these two molecules are going to be attracted to each other. And those little lines in blue I have there are just basically representing the attraction that these two molecules feel for each other. And that's because they're polar molecules. Now, if it's a really strong attraction, we have what's called hydrogen bonding. And most of you guys learned at least a little something about this in biology. So hydrogen bonding, strong dipole-dipole force. So it's still a dipole-dipole force. It just specifically gets its own name because it refers to a very strong dipole-dipole force, or a very strong attraction. So the common example that you'll see would be water, right? So if you have a water molecule, we know that it attracts other water molecules. That's why water beads up. That's why water dissolves ionic compounds, because it has these positive and negative ends. So if you draw the dipoles in water, they end up going towards oxygen, right? And that gives the water molecule a partially negative oxygen end, and then these two partially positive hydrogens, right? But if I have another water molecule, that means that that second water molecule is going to interact with the first one in a very specific way. It's going to line up so that the oxygens are as close to the hydrogens as possible. Because, again, it has dipoles as well, and an overall dipole towards oxygen. So these are both polar molecules, and they're going to line up to minimize repulsion, so that the hydrogens are not close to each other, so that the oxygens are not close to each other, but the oxygen and the hydrogen ends are close to each other. That, by the way, is why we call these intermolecular forces, because we're no longer talking about the bonds within the molecule. We're talking about one entire molecule and how it interacts with another molecule. Now, hydrogen bonding is unique in terms of dipole-dipole forces because hydrogen has a relatively low electronegativity of only like 2.1, whereas nitrogen, oxygen, and fluorine have uniquely high electronegativities. And so because of that big difference, these dipoles are greater than they otherwise would be. The actual magnitude of the dipole makes hydrogen bonding unique. It means that water molecules attract each other really, really well. The last type of intermolecular force that we'll talk about are called London dispersion forces, named after a guy, not the city. But these exist in all molecules, even nonpolar ones, but they're very weak. Okay, they tend to be very weak. We'll kind of adjust that statement a little bit later. But these are the result of electrons just randomly shifting to one side of a bond. And so, for example, if I have a CO2 molecule, and there's its Lewis structure, okay, and I know that this thing has dipoles. If I look up the electronegativities, oxygen is quite a bit larger than carbon. And so there's going to be these two dipoles, right? So that means that since they're heading in opposite directions, they're going to cancel each other out, and this is considered a non-polar molecule. So if you've ever seen dry ice before, that is just solid carbon dioxide. Well, you couldn't have a liquid or a solid of a non-polar substance if it could never be polar. In order for things to become liquids, they have to attract each other. Otherwise, everything that's nonpolar would be a gas. And if you've seen dry ice before, you've seen solid, so not just liquid, but actually solid carbon dioxide. So if it's nonpolar, how can it ever attract other carbon dioxide molecules? And the answer is to these things called London dispersion forces. So what happens is these electrons are in constant motion, and they're going to occasionally shift toward one end of the bond spontaneously. It just happens on its own. So you might end up with, for just a split second, or even less than that, you might end up with a polar molecule where the electrons maybe shift to the right, the way that I have the molecule drawn. And so what that's going to do then is that's going to make that molecule polar, just for a brief instant. But then if you imagine that that same sort of thing could also be happening in a nearby carbon dioxide molecule, that means that it's possible that just for a second they're both polar and they're both attracting each other in a very specific way. And it's temporary, right? So it comes and goes. It's sort of like flashing on and off all the time. And usually it's off, and usually the electrons are pretty well evenly distributed within a nonpolar molecule, but there's always going to be these little flashes of polarity, these temporary dipoles, you could call them. And it makes even nonpolar molecules have a certain amount of polarity. So everything, even a hydrogen molecule, which is, just two H's linked together by a single bond, can temporarily have a dipole. And so it is possible to have liquid hydrogen or even solid hydrogen. So these dispersion forces show up in everything, and they do also show up in polar molecules. So for example, there are dispersion forces in a carbon dioxide molecule, in a water molecule. It's just that usually, especially with small molecules, the dipole-dipole or hydrogen bonding forces are a lot greater than the London dispersion forces. So those are the ones that matter. So if I were to ask you what kind of intermolecular forces a water molecule has, you would say hydrogen bonding. Because yes, it does also have London dispersion forces, but they're so insignificant compared to the hydrogen bonding that we don't even mention them. But they are there for sure. So that brings us to, okay, so how does this affect the properties of a molecule? So if I have something that has high intermolecular forces, it's going to tend to have a higher melting and boiling point. So think about that. Why would that be? Well, if molecules attract each other, if we have high intermolecular forces, they attract each other, it's going to take a higher temperature to separate them. Slower rate of evaporation, which means volatility is just a word that refers to how easily a substance evaporates. A liquid evaporates, I should say. So if we have a liquid that has high intermolecular forces, it's going to evaporate slowly. Think about water compared to ethanol, alcohol. If you get hand sanitizer on your hands, it feels cold because the ethanol in that hand sanitizer is evaporating very quickly. And we're used to having water on our hands every time we wash our hands or get wet for any reason, and that evaporates a lot slower. So you don't feel the drastic temperature drop because evaporation is endothermic and takes heat with it. So hand sanitizer, which the active ingredient is ethanol, which has lower intermolecular forces than water, evaporates quickly because it has lower volatility. I'm sorry, higher volatility, because volatile means it evaporates quicker. So things like hand sanitizer have higher volatility because they have lower intermolecular forces. Another one is surface tension. So if you've ever done the little activity where you stack drops of water on a penny and see how many you can get on there, you've seen the surface tension of water, again, because it has hydrogen bonding. If you try to do the same thing with let's say, again, ethanol, there's not as much intermolecular force. You're not going to be able to stack as much. Your bubble is not going to be as big. Viscosity is just basically like resistance to fluids flowing. So if you think about like maple syrup has really high viscosity. So it doesn't flow very well. And if you have high intermolecular forces and the molecules are attracting each other really well, then you're going to have a lot of viscosity. The last one is they're likely to interact with other substances that have high intermolecular forces. So Anything that's got charge or partial charge is going to interact with water pretty well because water is polar. But it's not going to react with non-polar substances as well. So if you imagine, like, let's say you have the hood of a car that's been waxed, and you know it rains. You see the water bubble up on the paint because it's really bubbling up on the wax, and the wax is non-polar. So the water molecules, if we kind of zoom in on this, the water molecules in here are attracting each other. So there's a water molecule, here's a water molecule, and they're attracting each other much more than they are attracted to the molecules that make up the wax. So that's why there's no interaction here, or little interaction here, whereas if I mix water with something that's polar, then it's gonna interact a little bit better. So those properties become important because, you know, if you wanted to make a material waterproof, well, you're going to treat it with something waxy or something non-polar, because then water is going to beat up on it and not interact with it very well. The same thing is true when you put soap in water to wash your hands or to wash a shirt. You're lowering the surface tension of that water by interfering with that. The intermolecular forces between water molecules allows the water to get into spaces that it otherwise wouldn't, and clean your hands or clean your clothes better.